Hi everyone, we are Group 7 from Introduction to Statistical Economics Group B. There are 3 members in Group 7. I am Group Leader. My name is OOI XI HANN, metric number 310324. For question A, we are required to construct a 95% confidence interval for the mean quiz score. First, from the sample data, we obtain the sample mean x bar is equal to 69.167. The sample standard deviation S is equal to 7.938. The sample size N is equal to 24. Next, we determine the degree of freedom. The degree of freedom is N-1. Therefore, 24 minus 1 equals to 23 for a 95% confidence level and 23 degrees of freedom. The critical value from the t-table is 2.069. Next, we calculate the margin of error using the formula. Margin of error equals to t multiplied by s divided by the square root of n. Substituting the values, the margin of error equals to 2.069 multiplied by 7.938 divided by the square root of 24. This gives us a margin of error 3.352. Now we construct the confidence interval. The confidence interval formula is x bar plus or minus the margin of error for the lower limit. 69.167 minus 3.352 equals to 65.815. For the upper limit, 69.167 plus 3.352 equals to 72.519. Hence, the 95% confidence interval is from 65.815 to 72.519. We are 95% confident that the population mean quiz score is between 65.815 and 72.519. For question B, we are required to test the lecturer's claim that the average quiz score is 70 at the 5% significance level. First, we state the hypothesis. H0 mu equals to 70, H1 mu is not equal to 70. Since the alternative hypothesis, which is H1, is not equal to, this is a two-tailed test, the significance level equals to 0.05. Next, we calculate the test statistic using the one sample t-test formula. The formula is t equals x bar minus mu divided by s over square root of n. Substituting the values, t equals to 69.167 minus 70 divided by 7.938 over square root of 24. This gives t equals to negative 0.514. Next, we determine the critical value. The degree of freedom is n-1, therefore 24 minus 1 equals to 23. From the t-table, the critical value for a two-tailed test at alpha equals to 0.05 and 23 degrees of freedom is plus or minus 2.069. Now we compare the test statistic with the critical value. The calculated t-value is negative 0.514. Since negative 0.514, between negative 2.069 and positive 2.069, it falls outside the area of rejection. Therefore, we do not reject the null hypothesis. In conclusion, we conclude that the average quiz score is not equal to 70 at the 5% significant level. For question C, we are required to test whether the average study hours of the student is equal to 6 hours. First, we state the hypothesis. H0 mu equals to 6, H1 mu is not equal to 6. Since the alternative hypothesis contains not equal to, this is a two-tailed test. The significant level equals to 0.05. Next, from the sample data, we obtain the sample mean. X bar is equal to 6.167 and the sample standard deviation S is equal to 1.903. The sample size N is equal to 24. Now we calculate the test statistic using the one sample t-test formula. T equals x bar minus mu divided by s over square root of n. Substituting the values, t equals to 6.167 minus 6 divided by 1.903 over square root of 24. This gives t equals to 0.430. Next, we determine the critical value. The degree of freedom is 24 minus 1, which is equal to 23. From the t-table, the critical value equals to 0.05 for a two-tailed test is plus or minus 2.069. Now we compare the test statistic with the critical value. The calculated t-value is 0.430. Since 0.430 between negative 2.069 and positive 2.069, it falls outside the area of rejection. Therefore, we do not reject the null hypothesis. In conclusion, we conclude that the average study hours of the students is not equal to 6 hours.
Moving on to question D, looking at the data on the left of image, we have sample of 34 students total, divided equally into 12 males and 12 females. To tackle this, we follow a standard hypothesis testing procedure. For step 1 is setting up our hypothesis. The new hypothesis, HO, states that the mean score of males equal the mean score of female. Mu M equal to mu F, meaning there is no difference. The alternative hypothesis, H1, states that the means are not all equals, indicating a two-tailed test. For step 2, our significant level is 5%, that is 0.05. For step 3, we are using a two-sample independent t-test with a degree of freedom equal to N1 plus N2 minus 2, which gives us 12 plus 12 minus 2 equal to 22. Our critical t-value from the statistic table is plus minus 2.074. This leads to our step 4, which is decision rules. We will reject the new hypothesis HO if we compute t-statistic is less than 2.074 or greater than 2.704. On the right side of image, the initial calculation for the sample means by summing up the score of each group and dividing by the sample size 12. We find that the mean score for male students S bar M is 67.667 and the mean score for female students S bar F is 70.667. Now let's dive into the calculations of our test statistic as shown in the image. First, using a calculator to find the sample standard deviation based on the formula provided on the left. We get a standard deviation of 8.763 for the male group SM and 7.075 for the female group SF. Because we assume equal variance across the populations, we calculate a pool variance within our formula. When we plot our sample means 67.667 and 70.667, the sample size and our variance components into the pool test formula shown in the center column. The math simplified down nicely. The difference between our sample means gives us a numerator minus 3 after calculating the standard error in the denominator, which comes out to the square root of 10.592 and approximately 3.255. We divide these two numbers. This yields a final compute t-statistic of minus 0.922. Finally, let's look on the step 5 on the image, where we made our decision and interpret the results. To help visualize this, take a look at the normal curve plotted on the bottom of the slide. The shaded regions on the far left and right represent our area of rejection, AOR, starting at our critical boundaries of minus 2.074 and plus 2.704. Our calculated t-value of minus 0.922 falls right in the middle, well outside of the area of rejection. Because it does not cross into the critical region, our statistic decision is clear: do not reject HO. So, we conclude that there is no significant difference between the mean quiz score of male and female students at the 5% significant level. Thank you.
For question E, to test whether the mean quiz scores differ among students who use study method A, study method B and study method C by using one-way ANOVA. Since we are comparing the means of more than two groups, one-way ANOVA is the appropriate statistical test. The objective of this analysis is to determine whether different study methods lead to different average quiz scores. Specifically, we want to know whether the mean quiz scores for method A, method B and method C are significantly different. The first step is to state the hypothesis. The null hypothesis H0 states that all population means are equal. This means there is no significant difference in quiz scores among the three study methods. The alternative hypothesis H1 states that all means are not all equal. This means that at least one study method has a different mean quiz score. The significant level used is 0.05. This means we are conducting the test at 5% significant level. Okay, since we are using one-way ANOVA, the test statistic follows an F distribution. The number of group is K equal to 3. The number of observation is N equal to 24. Therefore, numerator degrees of freedom K minus 1, 3 minus 1 equal to 2. Denominator degrees of freedom N minus K, 24 minus K equal to 21. Using the F table with significant level 0.05, the F1 equal to 2 and the F2 equal to 21, the critical F value is 3.47. The decision rule is reject H naught if the calculated F value is greater than 3.47. Next, we calculate the mean score for each study method. For method A, 548 divided by 8 equal to 68.50. Then, for method B, 690 divided by 8 equal to 77.375. Then, for method C, 493 divided by 8 equal to 61.625. The grand mean is calculated by adding all score and dividing by the total number of observation. Therefore, 548 plus 619 plus 493 divided by 24 equal to 69.167. Next, we calculate the total sum of square or SS total. SS total measure the overall variation of all quiz score from the grand mean. The formula is SS total equal the summation of x minus x bar g square, where xg is the grand mean, which is 69.167. For example, for the first score, which is 68 minus 69.167 square. So the answer will be 1.361. For the second one, which is 72 minus 69.167 square, the answer will be 8.028. Then we will add all the square different for all 24 data. But to make it easy, we using calculator directly to get the answer. So the SS total is 1449.33. Next, we calculate the sum of square error, which is SSE. SSE measure the variation within each study method. The formula is SSE equal to the summation of x minus x bar I square, where x bar I represent the mean of each group. Same like the previous one, we calculate using calculator to easily get the value. Then we will obtain SSE equal to 551.747. Next, we calculate the sum of square treatment, which is measure the variation between the study method. The formula is SS treatment equal to SS total minus SSE. Then for the SS treatment, we will get 997.583. Now, we calculate the mean square. For mean square treatment, the formula is SS treatment divided by K minus 1. So, we will get 498.792. For mean square error, the formula is SSE divided by N minus K. Then, we will get 21.512. The F statistic is calculated by dividing MSD by MSE. So, we will get 23.187. All calculation can be summarized in the ANOVA table. Next, we compare the calculated F value with the critical F value. Calculated F value is 23.187. Critical F value is 3.47. Since 23.187 is greater than 3.47, the calculated F value fall within the rejection region. Therefore, we reject the null hypothesis. This indicates that the mean quiz score are significantly different among the three study methods. Therefore, at least one study method produces a different average quiz score compared to others.